Hi, my name is Brian Caffo, and this is a lecture on generalized linear models, binary data. This is co-taught with my co-instructors Jeff Leake and Roger Peng. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. Okay. Frequently, we care about outcomes that have two values. For example, if we're doing survival analysis, we're interested in alive versus dead, win versus loss, success versus failure, and etc. And these are called binary Bernoulli or 0-1 outcomes. The most common, let me expand on this. The most common version of binary outcome that I personally deal with is diseased or not. I tend to work a lot in developmental disorders, so the outcome that I might look into is something like a developmental disorder like autism or attention deficit hyperactive disorder. So that might be the outcome, and I might be interested in sort of how brain measurements predict those things. And then there's Bernoulli outcomes, which is just a 0 and 1. But if let's say if we flip a coin a couple of times, those are all exchangeable because they know none of the covariate values have changed. So instead of analyzing the individual 0 and 1s, we might analyze the count of 0s and 1s out of the number of flips, and that would just be called binomial outcomes. So the same model for Bernoulli outcomes kind of apply for binomial outcomes. So here's the Ravens data. Baltimore Ravens is an NFL football team located in Baltimore, which is the city that I live in and like very much. So you can get the data here, and you have to load it up by loading the data. And head just prints out the first couple of rows. Okay, so here's the variables, and imagine trying to fit a linear regression model to this. It wouldn't work very well, right? So here's a 0 or 1. If the Ravens won, we'd have an intercept, a slope, the number of points. So we're trying to use the number of points to predict whether or not they win, and additive error. So this, obviously doesn't make a lot of sense because, this additive error is going to make it so that this guy isn't 0 and 1 if the error is, say, continuous. Otherwise, the error would have to depend a lot on these values in order to make this always be 0 and 1. So here you can fit the linear regression. I don't think it's the particularly great thing to do. I would also say, by the way, it's not a horrible thing to do either. If you're interested in predicting a Ravens win versus a loss, and you just create a threshold linear regression estimate, this isn't the worst thing in the world to do. It's just not very interpretable, and right. And in this class, we're interested in interpretation. So if from a machine learning perspective, depending on the loss function, a linear regression might be perfectly reasonable for binary outcomes. But for interpretability, you want something different. So let's talk about things like odds, and this is a way to fit to reframe the model in a particularly interpretable way. So the binary outcome is 0, 1, whether or not they won. We could talk about the probability that they won given the parameters in their score, how many points they scored. The odds, remember, is the probability over 1 minus the probability. And the log odds is, of course, just the log of the odds, but the log odds is also termed the logit. I think a term that was invented by a person named Berkson, who was an alumni of my department a while ago. The department here is actually quite old. It's a 100-year-old department. I think it was the first department of biostatistics. So linear regression would do this, right? Directly fit the wins with an additive model, or you could just say the expected value. If we expect to value both sides of this guy, you get this equation because the expected value of the error would be 0. Logistic regression instead models this. The probability has to look like that, or this same equation rewritten is that we've modeled the log odds of the probability of winning given the score and the coefficients as being this linear predictor. And that's what we did exactly on the previous slide. So this probability, this probability right here we defined as mu I, and so this is log of mu I is equal to, and this is eta I right there from the previous lecture. Okay? There we have, now we have the equation rewritten. How do we interpret these guys? Beta 0 is the log odds of the Ravens win if they scored 0 points, right? Because if I just plugged in 0 there, that guy would go away and we just have beta 0. Okay? Beta 1 is the log odds ratio of win probability for each point scored. So let's just look at this, right? So we have what would be the so the log odds odds if they scored x plus 1 minus the log odds if they scored x would work out to be beta 1. Okay? And because this this is a subtraction of two right? It's the log of the odds, right? And because it's the subtraction of two logs, right? That's equal to the log of the odds if they scored. It's the scored is scored equals x plus 1. Point scored equals x plus 1 versus the odds if scored equals x. Okay. So that's why we consider it the log odds ratio. And then, by the way, is equal to beta 1. By the way, we can get rid of the log if we take e to this side. If e to both sides, we'd get rid of the log, and we get e to the beta 1. So e to the beta 1 is the odds ratio, whereas beta 1 is the log odds ratio. Okay? So if you want to interpret things back to the odds ratio. By the way, we don't have any other covariates here, but if we had other covariates, we'd have to add the phrase with all of their covariates held fixed. Okay, so let's talk about interpreting odds. Odds are very interpretable, at least as interpretable as probabilities are, and I like to think of them in terms of these gambling experiments. So imagine you're playing a game where you flip a coin that has success probability P. If the coin comes up heads, you win X dollars, and your opponent loses X dollars. If it comes up tails, you lose Y dollars, and your opponent gains Y dollars. So what should we set X and Y for the game to be fair? Well, what do we mean by fair? It means that your expected earnings and your opponent's expected earnings, which your opponent's earnings are just the negative of this. So if you set this, then they would be, you would do it for both, have to be equal to 0. Well, what is that? Well, it's you win X dollars with probability P, and you pay out Y dollars with probability 1 minus P. And we want that to be equal to 0. What does that imply? Well, that implies this equation right there. And so let's explore that equation. So imagine this. Imagine if X we arbitrarily set to 1, right? $1. Then and notice the right-hand side here is the odds. Okay, so so y over 1 equals odds, or in other words, if x equals 1, y equals odds. So in other words, the odds can be said as how much would you be willing to pay for a p probability of winning $1, right? Or how much more more or less than winning would you be willing to pay in order to win $1 given this particular game? Well, for the game to be fair, if you have a very high likelihood of winning, right, you should have to pay out a lot, right? Your opponent has a very low likelihood of winning, so you should have to pay out more. So y is going to have to be bigger. If p is smaller than 0.05, right, then you're going to have to pay out. Then you're going to get more, right? If you're betting on something that's really a long shot, right? If you're betting on something that has a very low probability of happening, then you should win more than the person who has a much more sure bet. And so, anyway, the odds are this ratio, and that's why when you go to a horse track, for example, they give you the odds of the horse, the odds against the horse. But the way you use that is it figures out your payout, right? If it's 10 to 1, then that means you're going to get, paid 10 times the amount that you're putting in. And so that's odds. And it's, odds are kind of uniquely interpretable, and they have all these other wonderful properties, like the log odds being the canonical link for the binomial Bernoulli GLM. Okay, well, let's look at what logistic regression is doing. So let me get my pen here. So just remember, right, that our logistic regression model was that the probability was e to the beta naught plus beta 1x over 1 plus e to the beta naught plus beta 1x. So this is a logistic curve, right? So the function, I don't know, I just call that p of x. So the plot of x and then p of x, right, is showing what kind of function we're fitting as the expected response is related to the predictor x, sort of the equivalent of plotting the fitted line in linear regression. And so this logistic function determines on beta naught and beta 1. So why don't we use our nice manipulate function to investigate what it does. So let me get rid of that text right there. So here I'm going to, here I have my, right here I just created an x, and it goes from minus 10 to plus 10. I've created my p, which is beta naught plus beta 1. Oops, I don't even really need that. Let me get rid of that. And then I'm going to plot x, and then p, which is this guy right here, and then I have some graphing parameters on this line, and then I'm going to tell RStudio to manipulate beta naught and beta 1. So let's do this. Oops. Okay, so here, if we look over here, here's our plot. So if I manipulate beta 1, it shows you that it increases the... Now a couple things to notice, right? Probabilities have to be between 0 and 1, so our curve is exactly, it has to go up towards 1. It has to look like an S, right? It has to go down towards 0 and up towards 1, or if our coefficient is negative, it has to start out at 1 and go down towards 0, but it has to look like an S or sort of a flipped around S like that. And as our beta gets closer to 0, right, this curve flattens out. It's always an S, but it looks like a line because we're sort of, but if we were to zoom out much further and have a larger scale of X, it would look like an S still. Okay, so, but if we get it at exactly 0, let's see if I can get it exactly 0. There we go. It's a straight line, right? And then, it goes, if we're on this side of 0, positive, the curve looks like that, and then if we're on this other side of 0, the curve looks like that. And so, and then what does the beta naught do? Well, it kind of shifts the S along. So see, there it is, as I move it that direction, and then there it is as I move it that direction. Okay. Now, one way to think about what's going on here, one way to think about what's going on, or not one way, the way to think about what's going on here, is for different values of x's, we have y's that are 0 or potentially 1 and 0. So you can think of sort of, this is the ideal case, right, where you had a bunch of zeros for x's at this value, and then it went up to 1 at this value. So if you had to fit a logistic curve, it would look something like that. So what it does is it sort of looks at the 0 and 1 data, and of course when we actually do it, you get some x's that are 0 over there, and you get some x's that are 1 over there, right? It looks at them and it uses the binomial likelihood to fit the best curve going through it, right? And then that curve will look something like that. So that's what logistic regression is accomplishing. So let's look at our logistic regression here and how we fit it. So here's our logistic regression for the Ravens data. We do GLM. Our outcome is a function of our score. So that's going to do an intercept plus the score, and this family equals binomial says that it's going to be logistic regression. And you can give a different link function if you want, but it by default assumes that it's a logit for the binomial. And then you can do summary, which will give you your coefficient table. By the way, you don't necessarily have to have use the $ to grab the column variables from that data frame. You can actually just put comma data equals Ravens data, and then you can omit that part and that part if you want. Okay, so then GLM tells you what formula you called. It gives you a set of a generalized form of residuals, a summary of the generalized form of the residuals, and then it gives you here's beta naught and beta 1. This guy is the log odds of the Ravens winning when they score nothing. So of course that's negative. When they score nothing, you wouldn't expect them to win. And if you wanted the actual odds of them winning, you would have to do e to the negative 1.68. And this guy is the increase in the log odds per every point that they score. And then e to that number is the increase, is the relative increase, the odds ratio for a 1 unit increase in score. And if we had included other variables down here, that interpretation would be holding these other variables constant. Let me point out something that kind of everyone knows when interpreting these coefficients. Often the coefficients are pretty small for whatever the reason. I think because lots of things we try to fit, if we knew the answer and they had these huge coefficients, we really wouldn't need statistics. We'd just know. So a lot of times these coefficients are pretty small. Take our slope coefficient, which worked out to be 0.1066. It turns out that e to the x looks like 1 plus x for x near 0. Near 0. And the closer you get to 0, the more accurate that approximation is. So you can, if this coefficient is small, like in this case 0.11, you can actually kind of just do the exponentiation yourself, and you know that kind of almost just represents the increase. If it's positive, the percent increase. So if you exponentiate it, you get 1.11, as we would expect, about exactly 1 plus x. And so we know that the Ravens are estimated odds of winning increases by 11% per point scored for the Ravens, is the interpretation of that model. Of course, this doesn't work so well for numbers that are not close to 0, like our intercept, which is negative 1. And you would like to interpret this as the odds of the Ravens winning when they score 0 points. But there is the issue that now, but how many games where they're in the data set where the Ravens actually scored 0 or near 0 points? And if that's the case, then just like with linear regression, the intercept is an extrapolation that you would worry about interpreting. Okay, so just to remind you to interpret this coefficient, it's going to be it's an odds ratio, so it's an 11% increase in the odds of winning per point scored. And then if you want to actually get a specific probability for a specific combination of covariates, you have to do e to the draw it again. If you wanted a specific probability, you would have to do e to the beta naught plus beta 1x hats divided by 1 plus e to the beta naught hat plus beta 1 hat x. And if you would plug in x there, that would actually give you the estimate of the probability rather than the odds. But if you just exponentiate, So here's the fitted probabilities. It has to look like kind of like a S-curve, which is what the inverse logit function looks like. And so what R is doing is it's fitting e to the beta naught hat plus beta 1 hat x over 1 plus e to the beta naught hat plus beta 1 hat x, and doing a range of plotting the observed x's, and they have to fall in this curve because that's what we fit, was this curve. So this, if you plug in a score, this is going to give you your estimated probability. Okay, so here's just getting the coefficients, which we already knew we could do anyway. If you, hang on, there we go. If you exponentiate the coefficients, you get what we thought we would see, about an 11% increase per point scored. You can exponentiate the confidence interval and then get the upper and lower bounds, which is a good thing to do. I prefer to do it this way just because I prefer to interpret the coefficients on the relative scale rather than on the log scale. Okay, so the ANOVA function works for GLMs. So if you do ANOVA of the fitted model, and this test equals chi-squared, we'll describe that in a minute. It gives you the model, in this case binomial, link is logit, tells you what your response was, and then if you fit multiple models, it sort of just like with linear models, it adds them sequentially. Ideally, you're doing this with nested models. Okay. So the deviance is, so the null model includes just an intercept, and the deviance is the sort of a measure of model fit compared to the previous model. So the degree of freedom equal 1 here corresponds to the one extra parameter we've introduced by including the slope. Okay. So the residual deviance is if subtracted, is going to give you the deviance, right? So if you subtract those two numbers, that's going to give you that guy. So that's how you compare deviances, is you take a smaller model and subtract from it a larger model. The difference in the number of parameters is the degrees of freedom, and that quantity then can be compared to a chi-squared distribution with this degrees of freedom. In this case, the chance of getting a chi-squared of 3.5 with 1 degree of freedom, that's pretty far out in the tail. There's only a 6% chance of getting one more extreme. So if I do 3.54 on the standard chi-square table, you get that's about 6%, and then that's about 94%. And you know that this is fairly large for a chi-squared statistic, because chi-squared with 1 degree of freedom is equal to the square of a standard normal. Standard normal, we know that out in the tail, there's about a 5% chance of lying above 2 or below -2, because that's what our confidence interval normal quantile we use is for a 95% confidence interval. And so if you square 2, you get 4, so you know that you knew ahead of time that this number was going to be about 5%. Okay. Okay, so let's just finish by talking a little bit about interpreting odds ratios. So odds ratios are not probabilities, which I think is clear, and odds are of course not probability, but they're a meaningful scale. We're not, we can't actually intuitively think of probability when, there's been lots of studies that show that people misrepresent probabilities, the probability of things in their heads, and they're incoherent, right? They don't think the probability of the opposite of something is 1 minus the probability. So So people have a hard time interpreting probabilities, and they have an equivalently hard time interpreting odds. I do like the one thing about odds in that I like the way it directly relates back to gambling and the sort of example we covered earlier. I think that's actually in the favor of interpreting odds. So an odds ratio, whether you wanted to look at relative odds or relative probabilities, you're going to find the same thing, that a relative amount of one implies no difference. So we estimate the model on the log scale. Then if we exponentiate the coefficients, we're looking for 1. If on the log scale, we're looking for whether the coefficients are 0. Right, and that's put right here. And so in our case, we specifically looked for the log odds ratio, but you could also look at the relative probabilities themselves, and that's called a relative risk. And there is it doesn't really satisfy the spirit of a GLM. There is something called relative risk regression, and that's when you want to interpret relative probabilities rather than relative odds. The problem with relative risk, the only problem with it, sometimes people like it better because people want to say there was a 10% increase in probability rather than there was a 10% increase in odds. Personally, I like the odds. But the problem with the relative risk is the log of the relative risk, so the probability is between 0 and 1. So when you log it, right, you get the upper bound is 0, right, and the lower bound is minus infinity. So we don't get the whole range, right? Whereas the logit function converts probabilities to a function on minus infinity to plus infinity. But so this creates boundary issues when trying to fit these models, and that's why relative risk models, in terms of writing the programs, and also when you have probabilities that are close to 1 or close to 0, you wind up with some problems. There's this famous result that says that you can approximate the relative risk with the odds ratio when the probabilities are the small. As Jeff wrote right here, they're not the same, but they can be approximated. And this is done so frequently in, say, the epidemiology literature that people don't even acknowledge that they're doing it. So the other interesting fact about odds, and I'll add this right here. So odds have an interesting use in retrospective studies. And what I mean by retrospective studies, so imagine if you're studying a treatment, or you want to study something like smoking, and you can't follow people prospectively over time. It takes too long. If you wanted to study smoking and lung cancer, you couldn't, say, follow people over 15 years and then determine exactly how much they smoked and then determine who, say, gets lung cancer or not. That's too hard. And a much easier way to to try and look at that would be to go to hospital records and get the names of a bunch of people who died from lung cancer and get their information, the age at which they died, and so on. Find some controls, maybe some matched controls, and look backwards. Maybe go contact their family or something, or something like that, to ascertain whether or not they smoked and how much. Or if you're not studying, you could go to live patients and get their smoking history. would be another kind of study you could execute. In both these cases, what you're doing is you're looking at the outcome as a fixed, non-random quantity. You sample 50 people who have lung cancer, or you sample 50 people who don't have lung cancer. And that number is non-random, but you'd like to treat it as if it was the outcome. Well, there's this interesting fact that you can use the odds to sort of treat that as the outcome, even though it was the designed parameter. And it's a little like flipping X and Y in a regression model, like where you've designed at specific values of X and Y as your outcome, and you flip it and treat X as the outcome and Y as the predictor. And it makes sense that would work, right, in regression, because the slope is really related to the correlation, and the correlation doesn't care which one is the predictor and which one is the response. Of course, the slope does, but the correlation doesn't. So it's a little like that. And it was kind of a big breakthrough in statistics because, for studying, and it did actually come about in the study of lung cancer and smoking. And what's interesting about it is the role that the odds play in those kinds of studies, in that this kind of ability in these binary models to flip the kind of to flip and get the kind of prospective interpretation from a retrospective study, that's uniquely determined by looking at odds. So, at any rate, if you're interested in that, that's not so much a data science topic as it is kind of a core biostatistics topic, but it's a really neat biostatistics topic. It was one of the key people who worked on that and discovered this was a person named Cornfield, who was sort of a famous former faculty from the Department of Biostatistics here, and he also worked at the National Institutes of Health in the U.S. Any rate, so if you want some further resources on this, there's a Wikipedia article on everything these days, but it turns out I find Wikipedia's technical articles actually often quite good. So they have an article on logistic regression, and it's good. The classic textbook on logistic regression is called McCullough and Nelder. Nelder, one of the two authors, both are great statisticians. Nelder, one of the two authors, was one of the authors on the original paper for generalized linear models. Anyway, that's the classic textbook that everyone loves. I was the research assistant for a person named Alan Agresti when I was in grad school, and his book on categorical data analysis I find to be a wonderful treatment of generalized linear models as they apply to categorical data like binary data, Poisson data, multinomial data, and so on. I give you some more links here. Jeff had written this slide, and he mentions I have some lecture notes on OpenCourseWare on Simpson's paradox, which is kind of related to confounding and the impact of confounding on model estimates. Case control studies, which we were just talking about, retrospective case control studies, and the textbook Open Intro has a chapter on logistic regression. All nice resources on logistic regression that you can look at. And I hope after this class you're able at least to fit a logistic regression, interpret the coefficients, and maybe do a confidence interval.